Hi, I'm Meryem. Please feel free to drop any questions or comments along the way, and I'll either answer them on the fly or we can do it at the end as well. So I'm Meryem. I'm the CEO of Doubleword. We're an inference company. Specifically, we focus on when people want to do large volumes of inference. So use cases like background agents, open cores, that kind of thing. This QR code will allow you to connect me on LinkedIn if you're interested. So I'm going to start with this graph, and I think this graph is probably one of my favorite graphs in all of AI, because I think it really shows us the rate of change that we're on in a way that is hard to measure in any other way. So this graph was produced by the Meetup organization, and on the y-axis, it classifies tasks by how long it takes a human to do the task. So starting at a couple seconds might be answering a simple question. Maybe at 10 hours would be something to train an image model, for example. Might be a task that would take a human that length of time. And the length of time it takes a human is a metric for the complexity of that. On the x-axis, you can see the date that the models have been released. And what you can see is that over time, we are producing models that are better, which is good. And better means they're able to do tasks that would otherwise take a human longer and longer periods of time. Now, this isn't a linear relationship. It's not even just an exponential relationship. It's an accelerating exponential relationship. So in this early period here, we saw roughly that every 7 months, the length of tasks that an AI model could do with a certain kind of accuracy would double every 7 months. So if in month 1, it could do a 4-hour task, in month 7 or 8, it could do an 8-hour task. However, what's really interesting is this rate of change is actually increasing. And more recently, it's become that every 4 months, the length of task it's doing is doubling. But you could really easily see how this extended over kind of a couple more years could have it being able to do incredibly ambitious things that would otherwise take humans months and months. This is like this idea of these long-running agents, or these kind of models that are able to run and solve really complex tasks, is often more easy to understand than with benchmarks. So with benchmarks, you can see a model accuracy going from like 92 to 93%. But actually, when you see the benchmarks laid out instead as the number of turns that a model can do without kind of making a catastrophic error, you can actually see that that extra percent means quite a lot. So if we move from like a 95 to 97% accuracy, you go from having to abort at step 5 to being able to have a model that can run for 9 or 10 steps, which is really, really impactful. And this kind of fits more widely into how I see that AI systems have been evolving. So we started in 2023 with chatbot style systems, which is single turn systems. You ask a question, it responds immediately to the human. In this, you might be producing kind of hundreds of tokens per interaction, so actually not that many tokens. We then very shortly saw RAG style systems and early tool use. So when you would ask a question, it wouldn't answer immediately. It would go off and maybe search something and then come back. Here we were using maybe thousands of tokens per query, but still not a lot. Then you got kind of early agentic things. And so deep research, I think, is a really good example of that, where you would have a model that could go off and do kind of complex tasks, reason in a complex way, search in a complex way, maybe using tens of thousands of tokens per step. And now we're seeing kind of the emergence of background agents. So these are persistent, autonomous, async, and these can produce millions of tokens kind of per human interaction. And as these models are getting better and better, these AI systems are no longer being what I call rate limited by the speed of human thinking. We don't have to check them every single turn. They're able to go off and really be able to do very, very complex things by themselves. And we should expect that this trend that I've laid out of increasing autonomy is something that will continue as models get better and better and better. A real world example. So Cursor built a browser with GPT 5.2. It ran uninterrupted for an entire week. So that is an AI system that is able to run for an incredibly long period of time by itself without making a significant error. And there's a bunch of use cases and examples from this that are you can see, especially big labs doing a lot of examples of. I'll skip through that. But the way that background agents work is you have some kind of trigger or human question, and it doesn't just immediately answer back like it would with a chatbot. It actually is a more complex series. The model can go off and do lots of interesting things. It can call other tools, it can call other models before it gives you an output or response. And each step you're doing is generating tokens. Now, I'm in the inference market, and so I'm interested in tokens and token production. And so maybe it's interesting to talk about what the anatomy of these longer running agents actually looks like. So here's a little calculator that we built. So let's think of a very simple agent. Maybe this is like a 5-step agent. It goes off and maybe it does like 5 things before it kind of comes back to you. This system is going to, hypothetically with these kinds of numbers, could cost you, let's say, 14 cents to run just one single request. If it's a more complex task, it might be, let's say, it does 15 steps, it could cost you 61 cents. If you're using something like Claude Sonnet and you're retaining all of the context. But as I increase this, you can see that the amount that it costs to host this agent and host every single query goes up exponentially, more or less. Now, obviously, you can use like a cheaper model, like a Qwen 3.5, and you can reduce the cost pretty significantly. But still, this is a very, very, very expensive system. OpenClaw, which I'm sure many of you have heard of, is a great example of this. It's just personal projects like doing things like email scanning, etc., can be costing many, many hundreds of dollars a month just for like individual personal use, which can get very expensive very quickly. And it's all running in the background. Now, there are a couple other things that mean that you'll end up using more tokens than just you're kind of going through lots of steps. One is that errors compound. So agents often go down the wrong path. Every time they go down the wrong path, they waste tokens, essentially. You can have various retry storms. So when you have tool failure, you'll have to retry all of those tokens, which happens quite a bit. And then you can also get kind of state drift. So the agent's memory will degrade over time as well, which can be very harmful for the number of tokens that you use. So the first takeaway that I want to leave you with is that async agents produce orders of magnitude more tokens than any previous generation of AI system. And as models get better and better, we should expect that they're going to continue using more and more and more tokens. More tokens obviously means exploding costs. So you could have a chatbot that would have cost fractions of a cent, and now we could have agents that are costing dollars per run. So for the rest of the talk, I'm going to talk about how you can reduce the cost of this and reduce the cost of your agents. So to do that, I'm going to talk about the very, very simple calculations involved, which is that your total cost, or the amount you spend on your tokens and the amount you spend on your inference, is a function of the tokens consumed. So how many tokens did it take you to do that request, and how expensive were each of those tokens. So I'm going to talk about 5 fixes for the token problem. The first 3 that I'm going to talk about is ways that you can reduce the number of tokens that you consume while keeping your application quality the same. And the second 2 is I'm going to talk about how you can reduce the cost of the tokens that you're using. So let's start with how we can reduce the number of tokens that are consumed in background agents. The fix 1 is that you can use checkpointing and state recovery to mean that you don't have to waste tokens. So in a system, and a lot of this is kind of very standard, good quality like software engineering practice, but it's interesting and worthwhile to know. Without checkpointing, you could have a system where, let's say you have a 50-step agent, or your agent has done 50 steps, and there's some kind of failure or logical error that happens at step, whatever, 40. You have to go back to the beginning and run it all again, which obviously harms both your latency and your costs. By implementing checkpointing, which is definitely something to recommend that we've seen, you can just go back to the latest checkpoint and rerun from there, and that can significantly reduce the number of tokens that you need to burn for your requests. The second fix that we would recommend is token budget management. So measuring exactly what you're spending on all of your tokens. So doing things like setting per task token limits, track per call consumptions, and also implementing early termination. For example, if a model is looping, you should stop it rather than kind of allow it to keep going. Fix number 3 that you can implement is a various form of context compression. So this exponential graph that I have here is assuming that I'm putting in the context of all of my previous steps into my next step, which doesn't always need to be the case. I can do things like context compression, where I, instead of putting all of the information into the next request, I can put in a summary of that, or I can put in just the relevant information that that particular task needs to know. And this exponential or extreme exponential here is if there's no context compression, but I can obviously, the more compression I do, then the less I need to pay for input tokens in later stages. It's also valuable to scope exactly what you're giving to your agents. So there's a school of thought that you can have some kind of monolithic agent where you have one agent that knows everything, or one model that knows everything, and it kind of just keeps working within itself and uses different tools, etc. Or you can have some kind of like hierarchical agent structure where I have some kind of supervisor agent, and then I have it can delegate to maybe more specialized agents that are doing more specialized tasks. So I might have one that's like a review sub-agent, and then it only needs the information from that. Also, these kind of agents that you delegate to normally don't need to be as smart as the higher up agent. And the impact of this can be pretty big. So if I have some kind of monolithic agent where the context accumulates, then every single token, I'm going to have this kind of ever-growing input tokens per step. But if I compress it, I hopefully can get it flatter and flatter. And so each extra step is more of a linear relationship than a non-linear relationship. So going back to those 5 fixes that I talked about, you can have, I've talked about the 3 fixes that will reduce the number of tokens that you need to put into an agent, but I haven't talked yet about how to reduce the cost of those tokens. So in order to talk about how to reduce the number of tokens, I'm going to talk about how the industry currently allows us to interact with AI APIs. And you currently have 2 options. One option is your real-time API, which is expensive, it's rate limited, it's fast, and allows tool calling. Or you can use batched APIs. And batched APIs are offered by most inference providers, and they typically give you 50% off, but to wait 24 hours. Neither of these 2 APIs is actually a good choice for background agents, and I'll explain why. So here's what we think background agents actually need. You need to be super low cost, so the tokens need to be really, really cheap because I'm generating a whole bunch of them. It needs to be not slow, and so I need to be able to complete multi-turn loops in minutes and not in hours. We need full tool calling support, so function calling and tool calling are non-negotiable because it's an agent use case. I need pretty elastic scale, so I can't be rate limited if I need to be able to scale up. And I need to be able to stream results. And we call this category of inference that the background agents actually need async inference. And this is a new category that doesn't really exist at the moment. And so we think that actually should be 3 types of inference. Real-time inference, which is great for chatbots, real-time coding assistants, etc. Async inference for background agents and other kind of use cases where there's multiple steps involved. And batched inference, which is great for like classification or extraction. Now, we think traditional batches are actually not done very well. And so what we've done at Doubleword is we've created the category of async inference and also improved the experience of you doing batched inference. And so if you have embedding workloads, classification workloads, background agent workloads, anything where you want to use inference at scale, we can be really, really helpful. And as a result, because we do this dedicated, we are very, very cheap, but have all of the ergonomics that you would expect from kind of your best inference provider. So this is for the same model quality. We are more than an order of magnitude cheaper than Anthropic, and that's Anthropic batch, not even Anthropic real time. So it's an incredibly cost-effective service. But you also get the ergonomics of things like streaming and tool calling, et cetera, et cetera. Now, going back to how we can make the cost of our tokens cheaper in background agents, we can do some kind of orchestration layer where I route to the right model depending on the class, on the task. So I can have an orchestration layer that will classify something into like maybe a real-time request or a non-real-time request. And when it's a non-real-time request, I can send it to my async endpoint that will process it a bit slower, or I can send it to my real-time request, which will be more expensive. Here's an example of how you might do that routing. This is like an instruction that someone gave their OpenClaw that they sent to us about routing to a real-time provider if the task is difficult and needed to be real-time, and otherwise routing to Doubleword. Another technique that you can use is what we call micro-batching. And so an old mental model of batched inference might be you do like really big jobs that's only worth doing if you kind of like a big bulky file. You can actually do what we call micro-batching, which is you do small batches on short SLAs with the same API, same models, and tool calling, but it's much, much, much cheaper and it's a much nicer user experience. It also means that I can do things like cancel paths that are no longer necessary if I'm an agent going down kind of multiple different lanes. Here is an open source project that we built that allows you to do this micro batching. It's called Auto Batcher. You can scan the QR code and use it, and it makes it really easy to use batched APIs, assuming you're starting from a real-time API. So I talked about 5 of the fixes for what I call the token problem, which is a problem that background agents, as they're getting good, are generating a whole lot of tokens. Going back to this graph, as I said, models are going to get better, and as they get better and better and better, we're able to trust them with longer and longer tasks, which is really interesting and opens up a whole new bunch of use cases, but also at the same time means that we're going to be spending a huge amount of tokens, and therefore we need to be smart about how we budget and manage those tokens. So key takeaways: agents consume an order of magnitude more token than traditional AI apps. We can reduce token count through various methods. We can reduce token cost through the various methods, especially picking the right API. Async inference is a new category of inference, a type of inference built for background agents. And Doubleword provides both async and batched inference optimized for agent workloads. Cool, that's me. And this QR code will take you to have some free tokens if you want to try out async inference for yourself and build some background agents. And we have some workbooks for building your own deep research bot.